All right, so continuing on discussing convergence, I want to be able to compare different spectral sequences. So we need to define a morphism of spectral sequences. And I think this came up already, and it's the obvious thing. We should just have maps that commute with everything, but let's make it precise. So a morphism of spectral sequences is what? Well, let's say it's a map from some spectral sequence, and I'll do this cohomologically graded, to some other spectral sequence. Oops. So this maybe has some different differential. We'll call that one E bar with D bar. Okay, so it's really just a sequence of maps. Those maps are bi-graded homomorphisms. And so each of those looks like, well, on each page, really this should go from ER PQ to ER bar PQ, but it should be a map of bi-graded modules, so I'll just write star star. Okay, and then it should commute with everything in the sense that if I do F after the differential, it should be the same as the differential after F, of course. Okay, and then maybe the one subtle piece here, and the reason that it's worth writing it out, is that this FR plus 1 should really be induced on cohomology or homology. Of course, I can make the same definition for a homologically graded spectral sequence, doesn't matter. But so the point is this should be induced from FR. So this should be compatible with taking cohomology and whatnot. Okay, so then we have this lemma that tells us that essentially if a map between spectral sequences is nice at some point, meaning gives us an isomorphism at some point, then it's an isomorphism forevermore. So, and that's where we really need that it's not just an isomorphism at each page, but it's compatible with taking cohomology to get to the next page, right? Okay, so let's let F be a map of spectral sequences. Let me just abbreviate that as E dot to E dot bar. Okay, so of course that's like star star and with their respective differentials, blah, blah, blah. Okay, so this is going to be a morphism of spectral sequences. And I want to say that we look at some rth page, and I guess I could say for all P and Q and write P and Q, but I'll just write star star. So we get to the other one. This should be an isomorphism. So let's say for some R. So it doesn't need to be an isomorphism on the second page or the first page, but if it's an isomorphism on the 10th page, well, then this lemma claims that we can go to any subsequent page and look at the induced map there, and that should also be an isomorphism. Okay, so that's for all n greater than or equal to r. And in fact, Weibel separates this out into two statements, but let's just go ahead and say it here. That also gives you an isomorphism on the E infinity page. Well, okay, the E infinity page isn't a page, right? So that one takes a little bit of proving. Maybe a little bit more than the other one does, but indeed that's also an isomorphism. Okay, great. So I won't really do the proof. I'm going to say this is a good exercise. It's not hard. And all you want to do here is use the 5 lemma. So that's a good one to make sure that you see how everything relates and sort of what the subtle issue here of saying this thing is induced what that all works out to be. If you get stuck, then you can find this in Weibel or McCleary, and most of it's written out in Weibel, and I think all of it's written out in McCleary, so feel free to check there. Okay, so what does that tell us? Well, maybe a good example is that if we have some map of spaces, say this is a map of CW complexes, then this is going to induce a map of spectral sequences. Say they come with some filtrations. This induces a map of spectral sequences. And of course it's going to go the other way because it goes the other way on cohomology, if we're talking about the cohomological spectral sequence. So here on the E1 page, we've got HP plus Q of YP, comma, YP minus 1, so for some filtration. And that's going to map to this other spectral sequence, which has on its E1 page the cohomology of the filtration quotients of X. And then, of course, that'll induce maps on all of the pages and maps on the E infinity page. And I wouldn't expect those to be isomorphisms unless these are homotopy equivalent spaces. Or I guess if they have the same homology, that would work too. Okay, so that's really nice. That's really telling us that this kind of spectral sequence is natural. And then, for example, in our Serre spectral sequence, I wanted to come back and address this at least a little bit since this came up in discussion. Though it was now long ago, you might not remember. So what does our Serre spectral sequence look like? I'm going to be kind of sloppy and assume that our base is simply connected so that I don't have to worry about local coefficients, but of course, local coefficients in the fiber, cohomology of the fiber, mapping to, or converging to HP plus Q of E, the total space. Okay, and what was the question that had come up? This seemed to depend on, well, really what did we do to build this? We found a CW structure for B, but that's of course not unique, right? So we found that CW structure of B, and we lifted it to the total space E, and we then ran our usual sort of spectral sequence to get the Serre spectral sequence. And then the key was to recognize, oh, that actually the E2 page had this nice form. We didn't have to go all the way back to the messy E1 page. Okay, so that's a little weird that it seems to depend on this, and I won't prove this in full generality that it doesn't depend on the filtration at all, but say we had some other CW structure on B, then the identity map is homotopic to a cellular map. And so that's going to give us a map of spectral sequences. And they'll have isomorphic E2 pages, right? Because our E2 page doesn't see anything about that filtration. And so they presumably don't have isomorphic E1 pages, but they have isomorphic E2 pages, and so the spectral sequences are isomorphic forevermore. Okay, I guess there's a little bit to check that this map really is going to induce the right kind of map so that as we go from page to page, that's all respected. But let me leave that as an exercise. Another good example, which we'll come back to, is if we had, say, some chain complex or cochain complex with some filtration, and we had a map to a different cochain complex with some other filtration. As long as this map is compatible with the filtrations, so that means that the induced map, I'll still call it F. It's a little bit lazy. I think, I was even kind of lazy about that too. Here I call this just F upper star. But okay, so coming from F, as long as this respects filtration so that FP on our first chain complex maps to the pth filtration of our second cochain complex, then this induces a map of spectral sequences. Okay, and so one of the games that we'll want to do as we're talking about convergence is compare spectral sequences, and this gives us a nice way to do that. Okay, so let's get back into convergence a little bit and remember where we were. I think this is last time. So we said that if we have, say, a cohomology spectral sequence, though again, the grading doesn't really matter, but we have some filtrations of the cohomology that we're trying to cook up. So that looks like not necessarily finite filtrations, but we'll write them as decreasing filtrations of Hn. This is just our usual thing. So I'm thinking of this as the cohomology of the total space or the cohomology of my filtered space that I was interested in, whatever situation we're in. So we have these filtrations for each n, and if we also have isomorphisms, identifying our E infinity terms, so that's isomorphic to filtration quotients, then we say the spectral sequence converges strongly. So that was really Weibel's converges, or Boardman's converges strongly. If what? Well, we needed this filtration to be good, and it was good in 3 ways. So I'll remind you what those are. So if the filtration is exhaustive, and that's a really easy fix, just take the thing that you're after to be the union of all the filtered pieces. And I feel like most other places aside from topology, somehow everyone assumes that a filtration is exhaustive, so that one's not such a big deal. We need exhaustive. We also need Hausdorff. Okay, so that told us that when we take the intersection of all these filtration pieces, that we get 0. Okay, so that's just because our filtration quotients would miss anything that was contained in that intersection. And then finally, complete. So complete, I think, was maybe the weirdest one, and we need to investigate that a little bit more, and we will in this video. But that was that really we should have this thing be the inverse limit of Hn mod the filtered pieces. Okay, and now we said at the very least that that's so that we don't have any lim1 terms. Okay, so let's see how that comes into play here. And to do that, we're going to start with a comparison theorem. I think this is actually called the comparison theorem in Weibel, though I may have changed the wording ever so slightly. So this is going to tell us how spectral sequences compare, not just if we have an isomorphism at some point, then it's an isomorphism forevermore, but also about what we're converging to. So let's take a map from some cohomology groups to some other cohomology groups. And I want this to be a special map. So really I'm trying to get myself into a particular situation. I'm going to say this map is, in Weibel's words, compatible with some spectral sequences converging to these things. And I'll spell out what I mean by that. So I've got a spectral sequence, and I identify some ER page and say, okay, that's converging to sorry, let me say H star. Well, I guess we'd normally write HN, that's fine. And then I've got some other spectral sequence. I'll just put a bar over it to say some other thing converging to this other cohomology group, H bar N. And what do I mean when I say that this is compatible? Well, I really just mean this induces maps, so it respects the filtration in particular. I'll still call these maps F, but they should probably have different names. I just mean induced by F. So let's call that F bar P H N bar. Okay, so this respects the filtration, so I've got these for all P and N. Then I should also have maps between the spectral sequences. So my ER page maps to my ER bar page. Got those for all R in the way that this is a map of spectral sequences. So, commutes with the differential and is induced. The one on the next page is induced by the previous one, okay? And then I also want that when I look at the E infinity term, well, saying this first spectral sequence converged to HN meant that I had this identification with this, with the filtration quotients. I'm following my usual convention that N here is P plus Q. Okay, but then I should have this map induced on the filtration quotients. So it should go over to F bar P, H bar N, mod the previous filtration. Okay, and that's of course identified with the E infinity term in my other spectral sequence, and I just want that F induces this map. Okay, so that's really for all P and Q, and I said this, but I'm following my usual notation that N here is P plus Q, so I don't have to keep writing P plus Q a million times. Okay, so this is our setup. We haven't stated the theorem yet. I'm trying to say I've got all of this data. I've got a map between two cohomologies, but it's compatible with spectral sequences. It looks the same on the E infinity pages. Sorry, not necessarily the same. I haven't said anything about isomorphisms yet. But just that's what it means to be compatible. I have these maps all induced by F. Okay, but now what do I want? Well, if I know the ERPQ and ERPQ bar, so my two different spectral sequences, maybe I should write that differently. Let's say, E and E bar. I just mean the whole spectral sequence. If these converge strongly, so that those filtrations are exhaustive, Hausdorff, and complete, so to H star and H star bar, and so I've got the best kind of spectral sequences, everything's compatible, and yet more if I know that my map from ERPQ, I really want for all P and Q, so let's just say star star. So my map on the Rth page is an isomorphism. Okay, of course that means that it's an isomorphism for all further pages and E infinity pages. Okay, so coming back up here, yes, I have identified these things. Okay, well then the claim is that not just on E infinity pages, but on the things you are converging to, you get an isomorphism. So that map we started with from H star to H star bar is also an isomorphism. Okay, so this all seems like a lot of, if this and if that and so on. But the point is that if I was looking at spectral sequences coming from spaces, and I had a map of spaces, that'd give me a map of spectral sequences, and it'd also give me a map on their cohomologies, and so on and so forth. And so a lot of this data sort of comes for free from just naturality. And then the whole point is if the two spectral sequences both converge strongly to different things, but they have, if the spectral sequences are isomorphic at some point, so in particular, they're isomorphic on E infinity pages, then actually the thing that you had the associated graded for, associated graded for filtration of their cohomologies, those cohomologies are also isomorphic. Okay, I'm not going to prove this either in the interest of time. I'm trying to do this whirlwind through convergence issues. So let me just say that you would want to use the 5 lemma and induction. And I think this is a good exercise too, but again, if you get stuck, this is in Weibel and McCleary. So maybe let me say see one of them or the other, or both if you get really stuck. Okay, but what's the point here? So the point, let's say the upshot at this stage, is that strong convergence actually tells us a lot. So we've said this is our best kind of convergence. There's no lim 1 term. But what we've also just said is that this gives us uniqueness of the target. Okay, well, I want to say a few words about that. So what this says is, if I have some spectral sequences that are induced nicely, so I've got some naturality or something like that, I can compare them nicely, and I get isomorphisms eventually, and so I have isomorphisms on the E infinity page, then actually I know that I was constructing, I know that these were associated gradients for filtrations of the same thing, even if they were different filtrations. Now, okay, they need to be sort of compatible filtrations. Remember, this was really a map of filtered modules and so on. So there's kind of a lot in here, but if you sort of take a step back and just think very broadly about what this is saying, it says we've got these two spectral sequences that converge strongly, and I get an isomorphism. If I have enough isomorphisms in there, I suppose, then I get an isomorphism on the targets. Okay, so not just the infinity terms, but actually the cohomology I was trying to build. Okay, so that's really useful because that tells us, yes, we really are getting the thing that we want. But it's important here, maybe let me just note that sort of, what did we need for strong convergence? Well, one of the big things we needed is completeness. And that, remember, was that our Hn was actually the inverse limit. That was sort of the funniest condition that we had, that was the inverse limit of Hn mod FPHn. That's the inverse limit over P, right? We're fixing an N here, but this should be true for each N. Okay, that's not really true. Of course, I still needed exhaustive, and I needed Hausdorff. And we'll see that Hausdorff is also sort of key here. I think I said exhaustive is kind of an easy one to get around, and I feel it comes up less of an issue. But remember, our Hausdorff said that if you took the inverse limit of all those filtered pieces, which is really just the intersection of all of them, then that should be 0. Okay, so we need that too. I mean, it's all in here, right? I'm saying strong convergence. I'm not, I don't want to forget any of those pieces, but what I'm trying to say is that sort of we have those 3 types of convergence from Boardman's terminology: weak convergence, convergence, and then strong convergence. And the thing that got us to strong convergence was this completeness. So that's what I mean by this is the key. Okay, so let's investigate that a little bit. I promised that we would. So how is this even showing up? I think I talked a little bit about how you could have lim 1, and so it makes sort of some sense that I might want this inverse limit condition to get rid of that. But maybe to go in depth a little bit more here, if I had some short exact sequence not really some short exact sequence, I just mean include one of these filtered pieces into the thing that you're after, and quotient, okay, that's a short exact sequence of R modules, and then remember that we could apply the inverse limit and we get an exact sequence where we have our 3 inverse limit terms and then our 3 lim1 terms. So maybe let me write applying the inverse limit. Okay, well, what does that look like? I take the inverse limit here, and I've got this inverse limit over P of FPHN. Okay, so that's showing up in my Hausdorff condition, that would be 0. Maybe I'll even write that since I'm saying it now, that's 0 if we're Hausdorff. Okay, that again, just the intersection of all of them. That should map to the inverse limit of the next spot. Well, I could give HN, I could make that a tower in the stupidest way, meaning I could do this just sort of for all P and it always maps to HN with isomorphisms everywhere. So, okay, this really just, the inverse limit is HN. It's not a very interesting inverse limit. Then I've got the inverse limit of this thing that we keep seeing show up in this completeness condition. So that's HN mod each of the filtered pieces, and we take the inverse limit of that. Okay, and then the next thing I should have a lim1 term, and I go back to the beginning, so that's the lim1 of FPHN. And then the next thing I have lim1 of this constant sequence. Well, there's going to be no lim1 term because they were all isomorphisms, so it's not very interesting, and so that exact sequence stops. Okay. Great. So, remember that we could have had 2 more lim1 terms, but in this particular case, because that's a constant diagram, it's not very interesting. All right, so this completeness thing is really saying that we have an isomorphism here, right? I keep writing equals, but of course I mean isomorphism. So this is if complete. And notice that if we have an isomorphism there, then yeah, our lim1 term vanishes. Oh, and also this other thing vanishes just because the sequence is exact. So, okay, that's why I said complete implies Hausdorff, the way we set this up. But alternatively, I could say, well, complete should mean that your Hausdorff and lim1 vanishes, right? Okay, so this is going to imply that this is 0. Okay, and then this piece in the middle, this is sometimes called the completion. Okay, I think I forgot to say the point of what I'm doing here. So we're trying to understand this strong convergence, and we said, okay, it gives us uniqueness of the target, and I want to investigate, what is this completeness really doing for me? And I guess I'm just trying to convince you from this diagram that yes, it really does tell me that lim1 term vanishes, and that also, yes, I should have that thing be 0. Okay. Great. Okay, so I said this is called the completion, and I think our notation is kind of messy, so I want to talk a little bit about the completion in general and what that gives us. So let's define completion first of all. I suspect that this is familiar to people, but just in case, let's be really explicit. So I'm going to take some filtered R module. Maybe let's call it M. So really I mean that there's M and it comes together with a filtration, and that filtration looks like the thing I usually draw. So I've got, we could index it however we want, but we'll just be consistent. FP plus 1 M sits inside the pth filtration, and so on. Okay, again, in algebra, people tend to sort of assume this is exhaustive, so just writing this even means that the union is M. But we're not assuming that here, though we basically could. So what's the completion? Well, the completion of M, I should extend that, it's really with respect to this particular filtration. Maybe you've heard about the P completion, of course, and then that's with respect to a particular filtration. That's sort of an obvious one. But so this is M hat for completion, and this is just defined to be this inverse limit that we keep seeing. So yeah, so M mod FPM. Okay, we take the inverse limit over P. All right, and then this comes equipped with a map. So there's a map from M to its completion. It's exactly this map that we saw here, right? Coming from the short exact sequence. So this is sometimes called the completion homomorphism. Okay, and that map is kind of nice. So maybe let me say, in fact, this completion homomorphism, it's really a map of filtered things. So I need to give a filtering on the completion. So I had M together with its filtration F, and this is really a map to its completion M hat together with a filtration of that F hat. And how do I get F hat? Well, F hat, hopefully there's no real choice here, right? So this is going to be the filtration induced on M hat by F on M. And what does that look like? Well, we take F hat, we take the pth filtration piece of M hat and define that to be the inverse limit, let's say over N of FPM mod FNM. Okay, so N must be bigger than P here for this to make sense, right? And so I take this inverse limit. Okay, so of course for, if P could go to infinity here, then I'm getting this completion. Great. Okay, so a proposition about how nice this completion plays with things is that the completion well, it's really this map of filtered modules. It's supposed to be a hat. It satisfies some nice properties. So the first is that, why is this called the completion? Well, the hope is that this is a complete filtration, and indeed it is. It's complete and Hausdorff. I think I said Hausdorff. Struggling with my tablet here today. Okay, and then, so that's good. It's got a good name. For all n greater than or equal to p, yes, really struggling. Okay, come on, Clover, we're almost done with this one. For all n greater than or equal to p, there's a nice comparison between the filtration quotients in the completion and the filtration quotients of the original thing. Namely, those are isomorphic. Okay, so that's nice. This completion does not change filtration quotients at all. And then the last thing that I want to point out is that f hat is exhaustive precisely when f is. Okay, so, well, okay, maybe let me say something about the proof and then talk about the point here. So I'm going to make the proof an exercise again. As I said, I'm trying to do this whirlwind tour through convergence issues, but this one is, I think, also in Weibull, but it's certainly McCleary proposition 3.12 if you get stuck. But none of these things are particularly hard. So if you're getting used to inverse limits and all this kind of stuff, these are really good exercises to do to make sure that you're following all the pieces. But okay, so what's the point here is that going from M to its completion, well, it's not going to hurt you if you were exhaustive. You're still going to have an exhaustive filtration, so that's great. This sort of induced filtration, you haven't messed that up. But now you'll have a complete and Hausdorff filtration. So that's great. That tells us that we're in the good case for strong convergence, right? And moreover, this piece 2 here is telling us you haven't messed up the filtration quotients. So for us, that's going to tell us we haven't messed up the E infinity page. Okay, so let me say as a corollary, and then this will be the last piece of this video, that if we had a spectral sequence and it is one that's converging weakly. Okay, so now I'm using weakly in Boardman's terms. So weakly to some groups Hn. Then it converges, I don't know if that needs a comma. A spectral sequence converging weakly to Hn converges strongly, well, not necessarily to Hn, that'd be too much to hope for, right? But it converges strongly to the completion. Okay, so the point here is that we can have the same spectral sequence. All we do when we talk about the thing that we see on the infinity page is say, oh, that's an associated gradient for some filtration of Hn. Okay, of course, that needs to arise in some sort of way, and that's part of proving that you have such a spectral sequence. But if you had a spectral sequence like that, then you could just take the completion of Hn. You take Hn hat, you're going to get an associated filtration, F hat, for that. You won't have changed the spectral sequence at all. You won't have changed the filtration quotients at all, so you have the same E infinity term, but now it converges strongly to this thing. Okay, so maybe there's some stuff to check that you can't have messed up anything in the spectral sequence along the way, but that's really the upshot here. So maybe one of the first big issues of convergence, well, okay, we saw there are a few things. One is, how do you get the E infinity term? And how do you know that you have something there that you can even identify? And then 2, how do you say anything about reconstructing Hn? Well, you have a chance of reconstructing Hn when you have strong convergence, so that you had an exhaustive Hausdorff complete filtration of Hn. And if you didn't have that, well, then complete the thing. Okay, and now you have strong convergence. You've got an exhaustive Hausdorff and complete filtration of the completion. You'll have the same filtration quotients, that same E infinity page. And now, how do you reconstruct Hn from that? Still got to solve all those extension problems, but you don't have to worry about any lim 1 terms. Okay, so what is weak convergence really going to give us? It's going to say there are more problems to solve than just the extension problems, going from these filtration quotients back to the thing that you filtered. All right, this video has already gotten kind of long, so let me stop there.